Hey guys, welcome back. So what did you learn in the last lecture? So we learned about the sound waves, right? So some of the things we learned in the last lectures. Let's review those quickly. So we said, what sound wave is, and then we looked at the audible range for human ear, which is from what frequency from 20 hertz to 20 kilohertz. 20 hertz refers to the sound with a frequency below 20 hertz is referred to as what? Infrasonic sound. Frequency above 20 kilohertz is referred to as ultrasonic sound. We also, we looked at this equation about how to find the speed of sound, sound, and then what are the characteristics or what are the parameters associated with the speed of the sound, and we found out that speed of the sound really be equal to square root of gamma kBt by m, where gamma is a constant for diatomic gas, monoatomic gas, it's gamma equal to 1.67. For diatomic it is 1/0.4, right? And then kBt was Boltzmann constant. T is the absolute temperature in Kelvin scale, and m is the mass of the atomic mass, right? And we said the acceptable value of a sound in speed of sound in air is what 343 meters per second, and that's basically at 20 degrees Celsius temperature. We also looked at these equations where we had sound intensity. Sound intensity is a ratio of a power per unit area, and then we also found sound intensity level or loudness of sound given by the quantity beta, where beta equal to 10 log I divided by I naught, where I naught is the threshold of hearing. I naught equal to 1 into 10 to the power minus 12 watt per meter square. This quantity is called this watt per meter square. It has a it has a special name called decibel. Okay, I think I forgot to mention about that yesterday. In the last lecture. So that is decibel. Okay, the watt per meter square has a special name decibel, and then represented by d lowercase d and then b. Okay, decibel. This is really after the name of decibel. Deci means 10, right? Bell is this word bell came from the name of Alexander Graham Bell, inventor of the telephone. Okay, so decibel, dB. So watt per meter square is also called decibels. So we also said one very interesting aspect of the sound is a Doppler shift or Doppler effect, and then we looked at the equation where when the observer is moving towards the source, then we have a frequency perceived by observer is given as by this equation here, where f observer O equal to fs times 1 plus b naught by or bo by b, right? And then if the observer is moving away from the source, same equation, the only thing that changes is instead of positive, it is negative, right? It makes sense. If the observer is moving away from source, this value of the perceived frequency must decrease, right? That's what this negative sign means, right? So that makes sense. Now, when we have both, so when we have source moving towards the observer, earlier we had the observer moving, right? Now the source moving towards the observer and away from the observer, we found this equation, and then if observer equal to Fs times 1 divided by 1 minus Vs divided by V, where Vs is what? Speed of the source, right, which is moving, and then V is the speed of the sound that the source is producing, okay? And then if this source is moving away from the observer, then what we have is just a change here. Instead of negative, we have positive, and if we put this together, we could just write, source moving, right, easy to remember. If the source is moving, then we have this equation here where negative plus, we can just write this combine, and then this upper sign, negative means, source is moving towards, positive sign means source is moving away, okay? So before so let's write this super and interference. So we are in a new chapter today. Think about this situation. You have been to the ocean, you have been to beach. What happens when two waves? One wave is like coming from this way, the other wave is coming from this way. What happens to the wave? The two waves when they meet each other. What do you think happens when these two waves meet each other in the space or in the place? What do you think happens? Give a moment to think about that. Okay, so keep that question, what happens to the waves when they occupy the same space, right, when they meet each other in a space. So here, when two waves occupy the same space, this is here we just have a water wave here, right? If you drop a stone in the water wave, I don't know, in the swimming pool, you would be able to see this, or even in the river, right? So these two waves, they are kind of coming together, right? This is a two-dimensional wave here. When two waves occupy the same space, they superimposed, okay? So super, super, and then impose, okay? Meaning they add together, okay? So superimpose, add, it means add, okay? Especially look at this imposed, right? Superimposed, so they add together. Now, okay, so if they add together, then what happens? Now let's go back to that situation where we have a wave, one wave, it's coming like this, it's coming this way in the ocean maybe, and then let's say we have another wave coming this way. What do you think happens? I'm going to try to make that diagram here on the board, okay? So we have some wave going this way. Let's say this is going this way. There is another wave, and this wave, let's say this is coming this way, right? Remember, so we can say really y1, really. Let's call this wave as y1, this is as y2. Remember, we can just represent like wave function, right, as y. These two waves, they are coming, right? As the time goes on, this is just a snapshot at some time, t, instant. As the time goes on, what happens? They get closer, right? They are like this. They are like this. Two waves coming, they are kind of, they are moving. As the time goes on, it's like this. But then look at this, the difference here. When my hands, they meet each other, look at this, they cannot pass through each other, right? Like, look at this, right? This is the physical object here we have. But however, when it happens with the wave, different phenomena happens. Okay, so what happens to the wave is actually, it turns out, this wave, when it gets here somewhere in between, it turns out that both of them add together. Okay, so it's kind of, it gets, and then what happens, the amplitude is like this big then. So let's say if we had amplitude, I'm going to just draw this here over this, okay. If we had amplitude, let's say A1, it has amplitude A2, okay, so this amplitude is A2. Then this, addition of this wave gives us that this amplitude is going to be sum of A1 plus amplitude is, high, right? Just add it together, and then this wave itself becomes new wave, which is y1 plus y2, okay? At some instant, at that instant when they are overlapping to each other. Remember, if it was a vector, it would get cancelled, right? But this is not a vector here. This is a wave. Okay? This is the medium moving here, right? So this amplitude gets larger. So instead of just one wave and it's going like this, they become just bigger wave. Okay, like that. So now, if we have both of these wave, they also have the same amplitude, and then let's say amplitude A1 and A2, they are really same. If they A1 equal to A2, right? Same. Okay, wavelength also. So if the wave has same wavelength and similar amplitude, then when they meet in space, when they overlap to each other in space, then they call something called a traveling wave, right? You guys already know, they call, traveling wave. But this is because of the two different waves, so this will produce something called standing wave, okay? So same wavelength and similar amplitude. So when they overlap, it produces standing wave. Okay? Alright, so, okay. This may be becoming a little bit abstract for you, so let's talk about this little. Yeah. Oh, yeah, I want to talk one more thing. Yeah. Okay, so if these waves are like this, right? One is going this way, the other wave, y2 is coming this way, so they are opposite to each other. When they meet in space, they form a larger wave, and the amplitude is given by the sum of the amplitude of the individual waves, right? Okay. So this amplitude is always larger than either of the individual wave. Okay. Now this type of effect, this scenario, this phenomena where two waves superimpose each other, and then they form a larger, they form a wave with larger amplitude. This is called constructive interference. Okay, so we are going to learn a new word here. So constructive interference. So this is an example of, this case is an example of constructive interference. Okay. Now there is also something called destructive interference. So destructive interference, constructive, they, construct, right? They formed. Destructive, they kind of did, see, right? From name itself, it's like something must be destroyed, right? Well, in theory, it's not destroyed like physically, but it is going to look something like this. So let's say we have one wave going, this way. Let's call this y1, and then this has some amplitude a1, okay? And then this is traveling this way, and then we have another wave like this, okay? The other wave is coming this way. So this is coming this way here, y2, okay? So this is A2, right? But A2 is negative here, right? It's down, so it's coming this way. So one is going that way, the other one is coming this way, but then see the shape of the wave is different here, right? Inverted here. So this type of wave, this is just a snapshot of wave at some instant t. As the time goes on, they're going to meet somewhere in between here, middle. And then when they meet, what happens is, what do you think happens? Destroys each other, at least from the name, right? So the resultant wave y1 minus y2 is going to be just nothing, as though they didn't exist. So that's going to be how, that's the, wave we will get here, okay? This is, of course, if they have the same amplitude, right? Because to get the amplitude a1 minus a2, to get the 0, we must have the same amplitude here, right? Okay? So assuming we have the same amplitude, then the resultant wave is this, okay? As though nothing existed there, but then, so that's when they meet each other. But after the time passes, what happens is this wave will continue to move this way, this wave is going to continue to move that way, and they regain their shape, okay? So this is very interesting, right? So for a moment it looks like they don't exist, but then after some time they, regain their shape, okay? So this is called destructive interference. So important thing is here, the amplitude of this resultant wave, right? Resultant wave is always smaller than the amplitude of individual wave which form this destructive interference, okay? Okay, so next topic we are going to talk in the next video, okay?